Hello everyone, this is Zidong with Ham here. Today we are going to talk about our journey of building high-performance mutable engagement data lake in Salesforce to support Einstein Analytics. So here is the agenda. First, we will cover what is engagement data lake in Salesforce and why we are building it. Then we will talk about the pipeline requirements and the design, like how we're gonna to support our customers incremental read and how our jobs achieve exact ones right across multiple tables in one transaction. After this, we will dig into the challenge of the handling mutations, including performance, tuning, benchmarking results. Lastly, we will keep some time at the end for Q&A. So first of all, at Salesforce, our customers are using high velocity sales to intelligently sell, convert leads, create new opportunities. So we built engagement activity platform to automatically capture and store our user engagement activities. The engagement activity platform is a key component to supporting Einstein Analytics, creating powerful reports, dashboards, Sales Cloud Einstein for training machine learning models. The large amount of data can only be scaled using engagement activity data lake, which built on top of a data lake. So here is one key use case of engagement data lake. For example, our sales rep can use engagement metrics, including number of engagement metrics, rates, to easily identify which kingdoms templates is more effective to run a campaign. For example, in engagement dashboard, we can easily get how many emails sent, opened, replied, discovered, and how many phone calls are meaningful contact or not interested, or left voicemail for any date, any sales rep. So we can leverage the engagement dashboard to drive intelligence into sales productivity. So with all these use cases from our product management, we convert them into our technical requirements. First of all, we need an independent string process to support engagement data lake, like a data lifecycle. And we have to have multiple downstream consumers. Some of them need incremental read, some of them require batch process read. So for example, one of our customers pull our data periodically to generate snapshots and build up engagement dashboard. Last but not least, there is unlike our immutable data lake we built before, the data in engagement is mutable, which is in a very high throughput and transactional, which is one of our biggest challenges. And one more thing, we have to make sure our data has to be consistency and has a very high integrity. And so all of these bring a huge challenge for us. So we will start with the high-level architecture. As you can see in this diagram, it includes three major components. One on the center is our data lake table, as you can see. And on the left is our injection jobs, which consumes engagement data through our internal Kafka queue and appending into our engagement data table. On the right side is our mutation component, which consumes the mutation request from the Kafka queue from upstream and apply the mutation to our engagement data table. On the top side is the pipeline that handle retention requests, which ensure all data policy for our customers. So with this design, Each stream processing is independent and has its own life cycle. So it comes to when it comes to our first requirement, the batch and incremental read. So the Delta API is quite powerful. It comes with the native support for batch read, such as time range query from T1 to T2, or organization layer queries like return all data for specific org. It also supports incremental read and return that returns all data since any checkpoint. But there is one prerequisite for this feature. It asks for the append-only data table. But remember, we just mentioned our table is mutable. So we will have to come up with our own design to handle the incremental read. So as you can see in the figure 2, we create a separate table called the notification table, which is partitioned by organization ID and injection time. So when engagement is generated into our data table, or when existing engagement data is updated or deleted, we will create a notification and insert into our notification table. Then we will notify our downstream consumers, say, oh, there is a new data coming in. Yeah, so we found there are many jobs can fit into this design pattern, like our mutation job, data retention job, or GDPR jobs. So we abstract this out and make it more generic. As you can see, we have this schema showing here. We use org ID as the partition key, and use engagement date as the query pattern. So, and the table name, which is what is the table this data writes into, and then last modified time. We also keep some counters like update, insert, delete for auditing purpose, and the app name, which app write into this notification. Yeah.
We also want to achieve a high throughput of transactions in engagement ID mutation, which is one of our critical use cases. What is engagement ID mutation? So each engagement activity has an owner. The engagement ID mutation is triggered when the role of the owner has changed. Take convert, for example, a lead L could become a contact C with a new ID, and all engagement that belongs to L will have a new engagement ID. Our engagement data table have 3 columns. The org ID, the engagement date, is the partition column, and the engagement is a struct with the engagement fields describing this kind of activity. Move to mutation request table. The column of org ID and the engagement date is used to join the partitions in the data table. The mutation operation could be either convert, merge, or delete. The key is the ID of the engagement identification, which is used to locate the particular engagement record in a data table. And the insert record is the new engagement activity record if applies. We have done the optimization at both data layer and application layer. So in data layer, we partition our table by org ID and Z order by engagement date. With this partition strategy, data are written to a partition directory of org and clustered by Z order column of engagement date. There are multiple benefits of this partition strategy. First, we can manage the granularity of a partition. Small files per org and date can be merged into a bigger one to help reduce the number of small files. And also, the data of engagement table are evenly distributed across reasonably sized files. Furthermore, we can tune the partition granularity with the config of max file size. We also optimize the query by IO pruning with data skipping and Z order. What is data skipping? Delta Lake automatically maintains the minimal and maximal value for up to 32 fields and store these values as part of the metadata. By leveraging the minimal and maximal ranges, Delta Lake is able to skip the files that are out of the range of the querying field values. So in order to make data skipping effective, data can be clustered by z-order columns so that the minimal and maximal ranges are narrow and ideally non-overlapping. These are the 5 examples from our data table. Take a look at the column of size. You can see that each file size is around 1 gigabytes, which indicates that the data are evenly distributed. Move to the column of minimal value engagement date and maximal value engagement date. The date range of each file you can see has no overlapping and is pretty aligned.
There is one more optimization we explored in the application layer to reduce the number of updates. As we just mentioned, mutation could be cascaded, and we will have to maintain the ordering of mutation requests. So in this example, user can change their ID, like workflow ID from 1 to 2 to 3 to 4 and so on. But eventually, the request just need to update their workflow ID from 1 to 4. But but in this case, we get 4 requests from the upstream. So we have to design an algorithm that can reduce, like pre-process those requests and reduce amount of requests. So here is the diagram, as you can see. We read from mutation table, get all requests, and group them by organization and sort them by mutation execution time. For each group, we use a Spark Graph API to build the direct graph, where the node is the ID and then the age is the request. And then we find all kind of connected components based on their graph direction, and find each node corresponding final state. So finally, we convert this subgraph into a list that can be passed into our Spark Delta query to update the data table. So with this optimization, we reduce a huge amount of unnecessary operations significantly, thus improve the performance. But we have one more challenge, and like how to ensure the high data consistency and integrity. So let's go through one example that we faced in our practice. So for example, our job, as we mentioned, writes into multiple tables in one transaction. So like the injection job will first write into the data table, then write into notification table. So what if first write succeed, then second write failed? Then our customer will completely lose the notification, so lost their data, right? So that becomes a very, very common problem across all of our projects designs, and then it need to be resolved. So we designed pipeline that we want to build we call it exact once write across multiple tables that requires like any writes into the table operation in transaction failed, it should not commit. And if there's any failed write, our job will only reprocess it. And so to achieve this requirement, we definitely need to save something, like some metadata similar as our delta log, which includes some state of each write and the last succeed checkpointing offset since our source is Kafka. So we create something called a checkpointing store that stores the start and end offset and some Kafka message, Kafka metadata, and the job last job state for given checkpoint. The first task of our Spark job is to read this store and get the last checkpoint in metadata and then the last job state. So let's go through this happy path flow first. As you can see on this table, we have 2 records, one for the same job, injection job. There are 2 processes here. One is the data injection process, one is the data notification process. And both batch ID are 10. So our Spark job will first fetch the batch ID from the Spark API and compare to this batch ID. If they are same, if they are matched, means our job completely succeeds in this run. So it will start pulling data from the Spark, our checkpoint store to get the new data from Kafka message and process all of them by the sequence. After all this, it will checkpointing back to the batch metadata store. And let's go through the unhappy parts. In this case, you can see the data notification process is batch ID is 9, which means it was not succeed in the last batch. So our Spark job will go to retry for this specific process by pulling from the Kafka for previously data and only process the data notification process. Then if it succeeds, it will checkpointing back with batch ID 10. So to kind of catch up for this last failure. So with this design, we are able to perform exact once right. And if there are any process failed, it could retry and only retry the specific process in the next scheduled job. No duplicates, right? No data lost.
In order to maintain a high data consistency and integrity, we came up with another design called global synchronization and ordering. Because our pipeline has multiple independent process strings, which concurrently write to the data table, it falls into the race condition model, where the shared resources are our engagement table, and the threads are the independent stream process. So we need a global synchronization to avoid conflicting commit. And we also want to ensure the engagement lifecycle ordering in our data process. And we want to apply the two in micro batch level. We create a job component. We create a component called job coordinator, which use the Zookeeper distributed log to ensure the global synchronization. And we implement the compare and swap to ensure the ordering. In order for the job coordinator to work, it takes 3 parameters. One is the log.name. It indicates what resources to protect. In this case, it is our data table. And it takes the name as a second parameter to indicate himself. And the third parameter is predecessor to indicate what job should be run first. With these 3 parameters, this is how the job coordinator works. First, the streaming job starts, and the job coordinator is initialized with a Zookeeper. And then it pulls the data from Kafka periodically and starts a micro batch process when message arrives in Kafka. Within the micro batch process, the job coordinator first tries to obtain a disputed log with the given resource name set in the log.name config. If they cannot obtain a log within a given name, it gives up. The next pull will start from the last checkpoint. Once it obtains the log, it reads the predecessor field and compares it with the expected one set in the job coordinator predecessor config. If the predecessor is not expected, it gives up its term, release the log, and the next pull will start from the last checkpoint. If the predecessor expected, then it just registers itself set in the job coordinator.name config. So after micro batch successfully obtain a log and validate the predecessor, it starts process and save the checkpoint when the process is complete. So with all these design in places, we did a performance benchmarking for our ID mutation job. We used a cluster of 32 nodes with the node type of I3 8x large, and we set the maximum file size equal to 128 megabytes. Then we are able to handle 28 million update and delete requests within 8 minutes. And finally, we listed all the blog posts and video recordings of our pipeline design in details for your future reference. And thanks for watching our sessions, and have a good day.